Okay, last video for our chemistry revision, and this one's on acids, bases, and special chemical reactions. We're going to start with what are acids and bases and what are some of the properties they have. An acid is a compound that contains hydrogen ions and a non-metal. So some examples are hydrochloric acid, the hydrogen ion you can obviously see, and the non-metal is chloride. And sulfuric acid, we've got two hydrogens and sulfur and oxygen atoms in the sulfate, that's what I was trying to say. Acids also donate hydrogen ions and have a strong concentration of hydrogen ions. They have a low pH, and their pH is less than 7. So the lower the pH, the stronger the acid. Also, a strong acid donates hydrogen ions very easily, whereas a weak acid does not. Also need to remember that acids are corrosive and they turn litmus paper red. Bases are the opposite of acids, and they can neutralize an acid to reduce its properties. Bases are often metal hydroxides, like here, so you'll see the hydroxide ion. Metal carbonates, oh hang on a minute, carbonates, there we go, and hydrogen carbonates, metal hydrogen carbonates. A strong base has very few hydrogen ions. A strong base is at pH greater than 7 and closer to 14. pH 7 is neutral. So an acid is less than 7, a base is greater than 7, and pH 7 is neutral. One other thing to remember, we often say alkali instead of base. Alkali is a base dissolved in water. Okay, so I've referred to pH a couple of times. So the pH is the concentration of the hydrogen ions. It tells you how strong or weak an acid and base is. So the larger concentration of hydrogen ions, the lower the pH. So that's a bit confusing, but an acid has a lot of hydrogen ions. So the stronger the acid, the more hydrogen ions it has, and the smaller its pH number. How can we test whether something is an acid or a base? We use an indicator. Indicates whether it is an acid or a base. So the two indicators we've used in class that you need to remember is litmus paper. Now litmus paper turns red in an acid and blue in a base. And universal indicator, and the benefit of universal indicator is it will tell you how strong the acid or base is, whereas litmus will just tell you if it's an acid or a base. Okay, so when you react an acid and a base, we call this a neutralization reaction. So in a neutralization reaction, acid plus base reacts to make salt and water. And you can see in our example here, our acid is hydrochloric acid, it's got the hydrogen ions. Our base is sodium hydroxide, it's got the hydroxide ions. It makes water, which is H2O, and a salt. Now the salt is going to be, you're going to recognize it as an ionic compound. Okay, so that will happen every time, with the exception of when the base is a carbonate or a hydrogen carbonate, you've got those carbon and the oxygen atoms there, so you also make carbon dioxide, which is a neutral product. So in this example, you've got nitric acid, there's your hydrogen ions, you've got sodium carbonate, and a carbonate is a common base, and you make sodium nitrate, this is our salt, ionic compound. You've got water, and you've got carbon dioxide, which is the result of having this carbonate ion here. So what you really need to remember is neutralization reaction. Acid and base makes neutral products of water and salt, and it will be a carbon dioxide on occasion if there is carbon and oxygen atoms in our base. Alright, another acid reaction is acid plus metal reactions. Now we know that acids contain hydrogen ions, so if you react an acid with a metal, you end up with a salt and hydrogen gas. So here's some examples for you. They're also displacement reactions. What's happening is the metal is displacing the hydrogen so that it becomes a metal salt and a hydrogen gas by itself. If you remember, displacement reactions is where the metals swap, and hydrogen is one of those unusual atoms that can behave like a metal in a compound. And this is just because it becomes a positive ion. So usually it is an actual non-metal, and non-metals normally become negative ions. Hydrogen's the exception, he becomes a positive ion. Anyway, acid and metal makes salt and hydrogen gas. Have a look at these examples. Magnesium's our metal, obviously. Our acid, sulfuric acid's got your hydrogen ions. When they react, the metal displaces the hydrogen and you end up with magnesium sulfate, that's our salt, and hydrogen gas. Alright, magnesium and hydrochloric acid, same situation. The magnesium displaces the hydrogen and you end up with magnesium chloride, a salt, and hydrogen gas. Sulfuric acid, got your hydrogen ions here. Zinc and sulfuric acid. Zinc displaces the hydrogen. Zinc sulfate and hydrogen gas are the products. Iron plus hydrochloric acid. The iron displaces the hydrogen. You end up with the salt, iron chloride, and hydrogen gas. So how are you going to recognize if you've got if you've got an acid-metal reaction? A single metal by itself, and your compound contains hydrogen ions. That's how you know you've got the acid. And you're always going to make hydrogen gas. The next set of reactions we looked at were exothermic and endothermic reactions. An exothermic reaction is one that releases heat into its surroundings. So that means the reactants had more energy, more chemical energy than the products. So that extra energy was released into its surroundings. So the couple of examples include any sort of combustion reaction, like any type of burning, any explosion, heat packs, and freezing. So if you're changing from one state to the next, where the second state has less energy, then it's an exothermic reaction. The opposite is an endothermic reaction. Excuse me. So the reactants actually have less energy than the products. So where does the extra energy come from? It comes from the environment. So the environment adds some extra energy so you can form your products. Now, if you're taking heat energy from your environment, that means it's cooling down. And that's how you can recognize an endothermic reaction. Some types of endothermic reactions include photosynthesis, so it requires energy from the sun in order for the reaction to occur. The use of ice packs, and melting. So it's the opposite of exothermic, where you go from, for an endothermic reaction, you move to a state that has more energy. So that would include melting, evaporation, and for exothermic, freezing and condensation. So on your test, you'll just be asked to recognize whether something's exothermic and endothermic by examples, and give some examples yourself. You'll also need to understand that an exothermic reaction, the reactants have less energy than the products, which is why the heat is released and why you get a temperature increase. And that for endothermic, the products have more energy, which is why energy is taken in from the environment, causing cooling down. Okay, we also looked at precipitation reactions, which are also double displacement reactions. A precipitate is a solid formed from two solutions. So a precipitation reaction is when we mix two solutions together and we get a solid. So if you have a look at our example, I've got potassium iodide being mixed with lead nitrate. When you mix those two clear liquids together, you end up with this yellow solid. And the yellow solid is lead iodide. In a double displacement reaction, what happens is we have two ionic compounds and we make two brand new ionic compounds. The A displaces with the C, so the two metals swap over and make brand new compounds. So the A will then pair up with the D, and the C moves over and pairs up with the B. So you end up with two brand new ionic compounds. Here's an example. So here we've got silver nitrate and sodium chloride. The silver and the sodium, the two metals, will swap over, and the sodium will pair up with the nitrate, and like so over here, and the silver will pair up with the chloride. So these are double displacement reactions. And in most cases, one of these is going to be a precipitate, so one's going to be a solid. How do you know which is a solid? You have to use something called a solubility table. So there's lots of different types of solubility tables. Here's an example of one. Soluble means it will dissolve, so that's the compound that will not be the precipitate. It's not the solid. It's the exceptions that are the precipitate. So here we've got compounds of nitrate. Nitrate is soluble. So that's not going to fall in the precipitate. There are no exceptions. Go down to sulfate, for example. Sulfate is soluble. Most sulfates are soluble except strontium sulfate, that's a precipitate. Barium sulfate, precipitate. Mercury sulfate and lead sulfate are precipitates. So this is how you read this table. Here are some examples of double displacement reactions showing the precipitate. So we use the downward arrow for our precipitate. So we have sodium chloride and silver nitrate. When they react, the sodium and the silver swap partners, and you end up with sodium nitrate. Now these guys are still showing the charge, but you guys know that you don't. And silver chloride. Now if I go to my solubility table, I've got a nitrate, and it says up the top here, nitrates are soluble. So that is not my precipitate. Let's go to chlorides. Down the chlorides, chlorides are soluble except there's your silver. Now since that's an exception, that's the precipitate, so that's why our downward arrow is after silver chloride. And it's telling you here it forms a white powder, white precipitate. Our second example, hydrochloric acid and lead nitrate. The two metals, swap, and I end up with nitric acid and lead chloride. Now, again, I've got a nitrate. It's soluble. Here I've got a chloride, I've got lead chloride. Double check. I go to my solubility table, chloride, and exception is lead, making that a precipitate. So that's why my downward arrow is there. Last example, same situation. I've got zinc sulfate and barium chloride. When they react, the two metals swap places, so I end up with zinc chloride and barium sulfate. So let's go to my chlorides up on my solubility table. They are soluble except silver, mercury and lead. Well, zinc's not there, that means that one's soluble. So let's go to my sulfate. Barium sulfate. Sulfates are soluble except there's barium, making that the precipitate. Alright, the last thing we looked at was single displacement reactions. It's similar to double displacement, except we have a single metal by itself. So it's a metal compound, an ionic compound, plus a metal, and the two metals swap places. And you end up with a new single metal and a new metal compound. Here's an example here. Zinc, my single metal, and hydrogen sulfide, plus hydrogen gas. Hydrogen acts like a metal, remember, and zinc sulfide. So the zinc is displacing the hydrogen. Here's another way you could remember it. It's just a funny cartoon. Oops, here we go. There's a single man and a couple, and she replaces him with this guy. So now he's single, poor Frank. So here are some more examples. I think we did the zinc one before, but zinc and copper sulfate. Zinc displaces the copper, and you end up with copper by itself and zinc sulfate. Got aluminium and copper sulfate. The aluminium displaces the copper, so I end up with copper by itself and aluminium sulfate. Iron and copper sulfate. Iron displaces the copper, so we end up with copper by itself and iron sulfate. And the last one, lead and copper chloride. Lead displaces copper, you end up with copper by itself and lead chloride. Okay, so that's it. Hopefully these videos help you. Your test is on Friday, first week back.